In this video, we will talk about probability. Probability is a really important topic and is at the heart of inferential statistics, which will be the bulk of business statistics. Even though we will not get into too much detail of probability, we'll cover three key topics in this lecture. We will look at some key terminology. Then we will look at two important rules in probability, the addition rule and the multiplication rule. And then we'll wrap up with a discussion of a very important theorem, which is used in machine learning based theorem. So in terms of what is probability, how do we define probability? Before we begin with probability, the key term is random variable. A random variable basically describes the outcome of a statistical experiment. We often denote the random variable by capital X, and once the experiment has happened and its outcome has been realized, we will denote that by lowercase x. So lowercase x is a particular realization of the random experiment or of the random variable. For example, let's consider tossing two coins, assuming that the coins are fair. X be the number of heads obtained. So our experiment is tossing two coins. Our random variable is number of heads we can obtain. The key idea here is to define the sample space. Sample space is the possibility of all the outcomes that our random experiment can take. So if we toss two coins, we could get two heads, we could get a head and a tail, we could get a tail and a head, or we could get two tails. So in our case, where our experiment is number or variable is number of heads that we flip, our random variable can have three realizations: x equals 0, where we do not flip any head; x equals 1, where we flip one head; and x equals 2, where we get two heads. A key concept is the idea of discrete versus continuous random variable. A discrete random variable is if we can count the outcomes of the experiment. For example, in our case, we are tossing or flipping two fair coins. And our experiment is number of heads we get. We'll get either 0, 1, or 2 heads. On the other hand, let's say that we're looking at the weight of players in an NFL team. We may have an upper and lower limit, but the actual weight can be anywhere on that interval by any decimal value. So it is very hard to count the actual weight that players' weights can take, so the actual number that players' weights can take. So this is a continuous random variable because we do not have countable outcomes. We have an infinite number of possibilities between any two upper and lower values. Probability is the numerical measure which measures the likelihood that an event will occur. Probability always ranges from 0 to 1, 0 meaning that the event will not occur at all, and 1 meaning that the event will occur with 100% likelihood. Even though we are talking with percentages, the convention is that we will use these in decimals. Probability density function is a function that describes the probability of a random variable. It has two key characteristics. The first is that the probability assigned will be between 0 and 1. And the sum of all the probabilities, or the cumulative, the fact that the experiment has happened, it can have any of the outcomes possible. The sum of all of these outcomes, the probability of all of these outcomes happening, has to be equal to 1. The PDF formula is the mathematical expression that calculates the outcome of any random experiment, and it's given by the number of ways. Let's say we're interested in finding out the probability of an event A occurring. It's given by the number of ways A can occur divided by the total number of outcomes. And we will look at a couple of examples to clarify this concept further. In the case of our tossing of the coin, it is often instructive to formulate our experiment in the form of a flowchart. So when we look at this, each node tells us what the outcome will be. We flip one coin, or we toss one coin. we can get a head or we can get a tail. If we get a head, we will be on this branch. Now, assuming that the first coin was a head, the second coin, when it's tossed, could result in a head again. So then our outcome is a head and a head. Or we can get a tail, then we get a head and a tail. On the other hand, if the first coin that we tossed was a tail, then we are on this branch. Then we come to this node at which we toss the second coin. The second coin can be a head or a tail. And this gives us our 4 sample points: head, 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 tail, tail, head, tail, tail. And the first letter denotes the outcome of the first experiment, tossing the first coin. The second denotes the result of tossing the second coin. An important idea, which is at the heart of calculating numerical probabilities, especially for outcomes which are countable, are the counting rules. Very often we're interested in selecting from a group of n objects a set of x items, and we want to know how many combination of x items we can get from n. So in this case, n is our total number of outcomes, or total number of objects, and x is how many items we are choosing one at a time. So the calculation that gives us the number of ways in which we can choose x objects from n is given by ncx, or n combination x. And it's given by, in the numerator, n factorial divided by x factorial times n minus x factorial. What is n factorial? So n factorial is essentially the number formed by multiplying n with n minus 1, n minus 2, all the way to 1. So for example, if our n equals 5, n factorial is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120 times 1. So this will be 120. And this is an important, useful formula for basically doing counting. So let's see an example of this. Let's say that we have a group of 6 letters, A, B, C, D, E, and F. I'm interested in drawing 3 at a time. How many groups of 3 letters can we form from a total group of 6 letters? So in this case, our n, which is our total number of letters that we are drawing from, is 6, and our x is 3. So in this case, the number of combinations will be given by ncx, which, as we've seen, is n factorial divided by x factorial times n minus x factorial, which would be 6 factorial divided by our x is 3, so 3 factorial times 6 minus 3, which is n minus x factorial. And then we can expand this. We get 6 times 5 times 4 times 3 times 2 times 1 divided by 3 times 2 times 1 for this 3 factorial, and then times 6 minus 3 is again 3, so 3 factorial, 3, 2, 1. And we can see that we can simplify some of these calculations by canceling out 3 with a 3, 2 with a 2. So what we essentially get is 6 times 5 times 4 divided by 3 times 2 times 1. So which is 6 times 5 is 30, times 4 is 120, divided by 6 would be 20. So we can form 20 groups of 3 letters from a collection of 6. Now, in this case, what we're saying is that the sequencing of these letters in that group of 3 that we draw does not matter. So what we're essentially saying is that A, B, C is the same group as if we had drawn B first, then A, then C, and so forth. But sometimes the ordering may matter. So if we consider A, B, and C as different than B, A, and C, in this case the sequencing is important, we call that a permutation. So the second counting rule is permutation. Permutation is when the order of selection matters. So we now have distinct groups from a collection of 6 letters. So we write this as npx, or n factorial divided by n minus x factorial. So unlike that combination where we had another factor, x factorial, we do not have that. So in this case, if we want to form 3 groups, a group of 3 letters from 6, but the sequencing matters, we are saying that we have 6p3, which now is 6 times 5 times 4 times 3 times 2 times 1. And we divide this by n minus 3, or 6 minus 3 factorial, which is 3, 2, 1. Again, we can cancel some of the common factors. So we get 6 times 5, which is 30, times 4, which is 120. So in this case, the sequencing matters. So for example, it says write all the permutations of A, B, and C. So we could draw A first. Or if we draw A first, we could get C and B and so forth. So we can just create all of these combinations. Then let's say we get B first, we could get A and C. If we get B first, we could get C and A. And then if we get C, we could get A and B, or we could get B and A. So each of these 6 combinations that we have, or 6 groupings, are all distinct because the sequencing matters. And this is what we mean by permutations. For simple calculations of permutation and combination, we can do it by hand, works well. But for more complicated numbers, we have a calculator function, but it's very easy to do this in Excel as well. And that's what I want to show. So suppose we still say that we have, let's say we have 20, or we have 15 items, and we want to draw groups of 5. So our n is 15 and our x is 5. So first, let's look at combination. Let's say I want to draw a group of 5 objects from a collection of 15. How many groupings can we have? How many combinations can we get? So the function for this is COMBIN. So COMBIN would be, it returns the number of combinations for a given number of items. The first argument in this function is the number, which is n. And then the second argument is, of course, I could have typed these numbers directly into my function as well, but it's always good to have relative references, because then if you change things up front, your values get calculated instead of hard coding it. And our number of items that we are drawing is 5. So 15C5 would be a big number doing it by hand, but we let Excel do it. It's 3003. What if sequencing mattered? So the first function for combination is COMBIN. For sequencing, the function is, unsurprisingly, PERMUTE. So we look at PERMUTE. It asks us for the number, n is 15, and our number chosen, 5. And here we get 360,360. So from a collection of 15, if we draw 5 and the sequencing matters, we can get 360,360 combinations. So when we assign probabilities, we said the 2 rules are that probability for a specific outcome from our set of possible outcomes that can happen is between 0 and 1, and that all these probabilities will add up to 1. So coming back to our coin toss example, we say that our sample space is getting a head and a head. We can get a head and a tail. We can get a tail and a head. Or we can get a tail and a tail. So now if our experiment was number of heads we get, we can say that x can be 0, can be 1, it can be 2. So let's look at the probability that our x is 0. That means we do not get any coin, so any head. So now we have not getting a head would be only this. So we have both tail and tail. So there's only one such outcome out of the possible 4. So our probability is 0.25. If our outcome of interest is x equals 1, then we have this case where we get the first head, the second is a tail, or this case when we get the first tail and then the second coin lands on a head. So we have 2 of these outcomes. Out of 4 possible outcomes, we have 0.5, and then the outcome being 2, we get 2 heads, or both coins show a face of head. Then we get 1 over 4 equals 0.25. And if we add 0.25 with 5 and then 0.25, we get that they add up to 1. Now, how do we assign these probabilities? In this case, we can look at the occurrences. We're assuming that each of these outcomes is equally likely, or we can collect the past data, and then we see that in the data, how frequently did an outcome arise. And that second is called experimental outcome. Now, there's a third outcome also. We call that subjective. Subjective probability is where we haven't seen the experiment happen in the past, but we are conjecturing or assigning a probability to the various possible outcomes. In the case of subjective probabilities, this is very common in finance, for example. Some may expect a stock to have a certain return, where some others may expect it to have a different return. In a subjective probability, people may have different probabilities about what the state of nature will be. So there may be a lot of variation. It's subjective again because it's probability coming from the investigator's own perspective.